All right. Good morning, physics students. Today we want to go over the solution set for exercise 4.1b, which is basically Newton's second law, where force equals to mass times acceleration. So let's start here. Let's get things set up a little bit. All right. So question number one: write the two common forms of the equation that relates force, mass, and acceleration. And the most famous way we are used to seeing this is force is equal to, let's type it all out. Force is equal to mass times acceleration. And so that leads to the abbreviated version. And let's go a little bit bigger today, a little bit bigger. There we go. All right, and let's change our spacing. I was doing a little bit of other work earlier. All right, so force is mass times acceleration. F is equal to ma. And the other way that's commonly used is when you want to calculate for acceleration, acceleration is equal to the force divided by the mass. Now our units, force is equal to newtons. Mass is going to be in kilograms, and acceleration is going to be in meters per second, -2 to the -2 seconds squared, meters per second squared. All right, so those are your two common forms. We've spent most of our lives looking at it. F is equal to ma. A number of people are preferring to see it A is equal to F divided by mass. And we'll use both forms of that today. All right, now the next several problems, I want you to get some intuition, about how the mathematical properties, how this thing moves around. So you can just begin to feel this rather than have to crunch a number anytime. So question number two, if mass is doubled in a problem, what happens to the force if acceleration remains constant? All right, let's go ahead. And so we are calculating for force. So we want to use this version, F is equal to ma. And then let's set up a simple problem. Let's go with force is equal to, let's say 5 kilograms. And for speed, I'm going to just drop the units. So our mass is 5 kilograms and our acceleration would be 10 meters per second. And that would give us a final force of 50 newtons. All right, so what would happen if we were to, we're going to double the mass. We're going to double the mass and keep acceleration constant. So now we have 10 kilograms. Acceleration remains the same as 10 meters per second squared. And so our new number is 100 newtons. So we have doubled the force if we double the mass. All right, if the mass is halved in a problem, what happens to the force with acceleration remaining constant? And let's see, let's set up force is equal to, let's go with 20 kilograms times 10 meters per second squared. And so we have an initial result of 200 newtons. All right, now we're going to half the mass. So force is now equal to 10 kilograms times 10 meters per second And so we see that by having the mass cutting in half, we now have a result of 100 newtons. So if the mass is halved, then the force is halved also. All right, now this one's not quite as intuitive. If both mass and acceleration are doubled in a problem, what happens to the force? Okay, force, let's set up, let's start with our 10 by 10 here. Again, that's pretty easy numbers to work with. So we've got our 100 newtons again. And so force, now we're going to double both of those at 20 kilograms and 20 meters per second squared. And so we're now up to 400 newtons. So if we were to double both, we would have a result 4 times as high. Okay, let's see now. Oh, we're switching over to acceleration. So we're calculating for acceleration in number 5, and we're going to double the mass, and the force is going to remain constant. So let's set up our basic equation. A is equal to force divided by mass. And let's see, what kind of numbers do we want to put in there? A is equal to, well, let's stick with our 20, force of 20 newtons. And let's put the in there just so it's a little easier. 20 newtons, and our mass is, let's say 10 kilos, 10 kilograms. All right, so our result is going to be 20 divided by 10. Our first result is going to be an acceleration of 2 meters per second. This just takes a little bit longer to type out. Per second squared. So now we're going to set up a new problem where the acceleration is doubled, or I'm sorry, the mass is doubled. So we have 20 newtons again. We're dividing that now by 10 kilos. 10 kilograms. And so our new result is, we need to double that. Sorry, need to double. We've doubled our mass, so our new result is 1 meter per second. All right, so if we double the mass, acceleration goes to 1/2. So if we double the mass, we half the acceleration. All right, so this time we're going to double the force in number 6. We're going to use that same equation. Again, that's a very handy form of it. So we're going to double force. All right, so A, let's start out with, let's do our 20 newtons again, and we'll do 10 kilos again. And so our answer there, the acceleration, is the same as above, 2 meters per second squared. All right, so now we are going to double the force. So our new problem is 40 newtons, and 10 kilos remains the same. So we are at 4 meters per second squared. I need to get some sort of shortcut key for that. But anyway, we have doubled 2 times. The acceleration doubles when we double the force. When we double the mass, we decrease our acceleration by half when we are doubling the force. We've doubled our acceleration. All right, so this linear relationship. All right, let's see, 2x, and let's get rid of that. What is the acceleration of an object if a force of 20 newtons is applied to a mass of 2 kilograms? So we have a straightforward, so acceleration is equal to straightforward calculation, force divided by mass. And so acceleration is equal to 20 newtons, and our mass is 2 kilos. And when we divide that, we have an acceleration of 10 meters per second squared. All right, so that's just a straight forward calculation. These others, 2 through 6, were to give you this intuition of, as we are doubling or having forces and masses and accelerations, etc., what's going on? Just want you to see that basic relationship. All right, and let's see. Here is a straightforward F is equal to ma calculations. Force is equal to 5 kilograms times, and let's just put that in parentheses, times an acceleration of minus 9.8 meters per second. Boom. There we go. And that's going to be equal to 49 newtons when you run that math, 49 newtons. And if you notice, the negative 9.8 equals the acceleration due to gravity. And you notice that it is a minus 9.8 meters per second, and that indicates that it is a falling object. All right, let's proceed into 9 and 10. We're going to need to raise our work here a little bit so we can get to it. 1 second, please. 1 second. All right, let's do a quick file save so that, hang on, let me save that as solution set 1 rev. All right, thank you for bearing with me on that. And let's see, let's start up with a new layer here. All right, got a little bit of room, we can go a bit larger. Sorry, forgive me while I tweak. All right. Okay, so we have a rock here. We have a rock that's being pushed with a force on the left-hand side of 15 newtons. It's a force of 15 newtons to the right. And on the opposite side, in the opposite direction, we have a force of 10 newtons to the left. And if you notice on that graphic, it is a minus 10. I know that's a little hard to see. But in these cases of opposing forces, or let's say the 10 newtons was pointing the other way, the additive forces, we simply add or subtract the forces at hand. All right, so the force, and we're going to need white type. The force total is going to be equal to the 15 newtons going to the right plus, because it is actually additive, we're the minus 10 newtons, which is pointed to the left. And then when we sum that up, we have a total resultant force of 5 newtons. Those problems are that simple. If both forces had been in the same direction, well, we can do that real quick. Force total would be equal to, so we've got our original 15 newtons going to the right. And let's say we swap that 10 Newton force that's going to the left, and we switch it over to 10 newtons to the right also. Then we have a result of 25 newtons pushing on that rock. All right. And let's see here. Okay, so I hope that's clear. And then finally, we need a little bit of trigonometry on this last problem. We've got a rock, different rock, and we have our 20 newtons to the right again. Well, we have 20 newtons, and they're going to the right. Force total again. And so that's pretty clear. We know that we've got the 20 Newton force going to the right. But how do we deal with this force of 10 newtons that's at a 30-degree angle? All right, so we need to do a little bit of trig, So let me just extend this problem a bit. So we've got our 20 newtons, and the way we treat that 30-degree angle, we treat that 10 newtons as the hypotenuse, and we are looking for its resultant force in the x direction. And so our math for that becomes 10 newtons times the cosine of 30 degrees. Cosine of 30 degrees. And so that's our math on that. All right, so when we look up, so we have 20 newtons again, and so that becomes, the 10 newtons stays the same. The cosine of 30 degrees in decimal form is 866. I like working with decimals. And then so our final result, when we multiply that all out, is 28.7 newtons. And again, so this is our force. This is our force total that's all moving in the x direction here. You see my little cursor moving there. So there's a total force pulling that rock to the right of 28.7 newtons. And we got there by calculating the cosine of 30 degrees, taking our force at the 30-degree angle of 10 newtons, multiplying that by 0.866, coming up with a final value of 28.7. And so there we have the answer set to 4.1b, Newton's second law, force is equal to mass times acceleration. Thank you so much, and I hope you all have a good day.